Hey there, Stats. Yesterday, we were looking at residuals, and, there's not a whole lot you can say right off the bat with residuals, but today we're actually going to see what are residuals good for other than pure computation. So taking a look at today's lesson, we've got iPhones. How many iPhones will be sold? And so here's a data of iPhone sales during their opening weeks. You can see that during their opening week, the very first iPhone sold in 2007. On its first week sold 500,000 units. That's 500,000 units. The 3G in 2008 sold 1 million. The 3GS in 2009 sold 1 million as well on its first week. So kind of the same, really. When we got to the iPhone 4, we've got 1.7 million sales. And then there seems to be a really big jump here because the 4S sold 4 million, and et cetera down the line. By the time we get to 2015, the iPhone 6S and 6S Plus sold 13 million units. So the first thing here is to create a scatter plot with the year as explanatory variable and the units sold as response. Here's that data, and you should notice something distinct about this. If I try to draw a straight line here, well, it does show the increase, but it doesn't do such a good job down over here. It does a great job here at the beginning, great job here at the end, doesn't do so much of a good job here in the middle. In fact, if you looked at this, a better description might be this curved relationship. So when we describe the form of this distribution, linear or nonlinear, we're correct in saying that this is a nonlinear or perhaps a curved relationship. So even though it's curved, even though I know it's curved, I'm going to break the rules here and try to make a least squares regression line. It's not going to work, right? This is a curved data. A least squares regression line is straight line data. Over here on Staplet, if I go and create that model, yeah, exactly what we thought. It kind of goes through here, but it catches the end, catches the beginning, doesn't really catch the middle very well. Down over here we have X equals year and Y is units sold, and this gives me my equation over here. Negative 3,222 plus about 1.6 multiplied by the year. Here we have that graphed with the line. Let's calculate the residual for the year 2007. The residual is equal to actual minus predicted. The actual is 0.5. The predicted is at negative 3,222 plus 1.605 multiplied by 2007. That gives me 1.8978. All right, so what we can do now is, since we have all of this, we can actually fill out this table here with the predicted and the residuals. We'll take a minute to do that. With those values, we're going to create what's called the residual plot. So we'll do a few of these with you. The first thing to do is to locate the residual and the year. So in 2007, the residual was 1.9. So we're going to put a point. X coordinate is 2007. Y coordinate is the residual, which is 1.9. Just like that. And we're going to continue to put the points. The next one is 2008 and 0.79. Continue. And that completes our residual plot. Now, there's a few things that you can see here. The first thing is if we group the points by where they are with their y coordinate, we can see for these first two coordinates, the actual value was greater than the residual value. Then we have a few coordinates where the actual is less than the residual. So actual minus residual is a negative value, followed by a couple more points where the actual is greater than the residual. So the residual pattern is positive, negative, positive. Okay. So since we have that pattern in the residuals, anytime we see that positive, negative, positive pattern, or even a negative, positive, negative, that means that the linear model is not a good fit for the data. Anytime you have a residual plot where there's an obvious pattern, usually it's a positive, negative, positive, or negative, positive, negative pattern, the data that you are trying to graph is a nonlinear data. That's what's good about the residual plot. It exaggerates these patterns and makes it easier for us to decide whether or not the data that we're trying to plot is linear or not, or if the linear model is a good fit. The residual plot tells us if the linear pattern is a good fit. So that's what that residual plot is good for. Hopefully we can compute all of this using, you can plot all of this just really simply. And it's time for us to take a look at our learning targets. Number one, we're using the word least squares regression line. And the least squares regression line, which we'll learn to calculate later, is a line with the smallest sum of the squared residuals. So if I add all the if I square all the residuals and I squared them, the line that you can create with that smallest sum is going to be called the least squares regression line. I like to say it's the official regression line for AP statistics, but really it's the official regression line for everything, any kind of data analysis that we do for a linear pattern. The second learning target here is that residual plot. We want to make sure that the residual plots show a random scatter without an obvious leftover pattern. You'll hear that leftover pattern a few times. It really doesn't mean a whole lot. You really don't even need the word leftover in order to make sense of that. So here's a couple of examples. The first one over here on the left, this pattern or this residual plot, that doesn't show an obvious pattern. It's just a random scatter of coordinates. However, this second one over here, that shows a positive, negative, positive pattern. So the least squares regression line or any linear regression model is not a good fit. Let's check our understanding. We're going to take a look at 9th grade students at web schools. They're going to go backpacking every fall. Students are divided into hiking groups of 8 by selecting names out of a hat. They don't get to pick their friends, so that's interesting. Oh well. Before leaving, students and their backpacks are weighed. This is a big deal when you're hiking, and your backpack needs to not be so heavy. You definitely don't want a heavy backpack. The lighter you can get it, the better it is when you're backpacking. That's just a little backpacking deal. So here are the data for one hiking group, and we're going to calculate the equation of the least squares regression line. Now, to do this one, we're going to practice with the TI-84. With our TI-84, we're going to turn this sucker on, and then we're going to go to Stat, Edit, and now that we have nice, clean lists, we're going to put our data into the lists. Here's our body weights. Hopefully, when we do this, our, the people with a higher body weight, they're going to be carrying a heavier backpack. That's generally the way things go. Now, the very first time you make a linear regression on your calculator, and I think this is the first time we've done an LSRL in AP Stats, you're going to want to click the Mode button and scroll down so that you go to Stat Diagnostics right over here. It's defaulted off. You want to turn those on, and that's going to give you the values of R and R squared. Notice up over here it says display the correlation coefficients. So that's exactly why we want the Stat Diagnostics on. We'll quit to the home screen, and we're going to click Stat, Calculate, and we're going to do number 7. Number 7 is the official linear regression for AP Statistics. Okay, don't be confused. Number 9 looks like linear regression, but that's actually a logarithmic regression, natural log regression. Linear regression is number 8. So I'll click that, and I get a wizard here. The first thing it asks for is a X list, then a Y list. Change those accordingly. The next one is a frequency list. We are probably not going to deal with frequency lists, so just leave that blank. Store regression. This is good because it'll allow you to use that regression later. I'll go ahead and store that in Y1. So I'll push alpha trace and put a Y1 there. And then I'll calculate. Okay. Now it gives me my value of A, B, and my value of R squared and R. I'll just need to write those down on my paper and I'm good to go. Just like everything else in AP Statistics, we know you have a calculator. We know you're using a calculator. You don't have to tell us what you're putting into your calculator. Just write down this least squares regression line. Okay. Next, we're going to make the residual plot for equation 1. Okay, so I'll show you a couple of things here for making the residual plot. So what we can do for the residual plot is go to Stat, Edit, and over here in List 3, we can make this the value of our residuals. So what is the definition of the residuals? Well, the definition of the residual would be the actual minus the predicted. Where are the actual values of the backpack weights? Well, they're in L2. So I'll just click over and put an L2 there. Minus, now how do I calculate the predicted value? If you remember, I put the regression line in Y1. So if I call Y1 here, and into Y1 I substitute the values of L1, that will give me the predicted values. So go ahead and take a look down over here. L2 minus Y1 evaluated at L1. Push enter, and that should give you all of the residuals. Okay. Now that I have the residuals, I can go to Stat Plot, look at plot 1, and instead of plotting L1 with L2, I want to plot the body or the body weights, which was L1, against the residuals, which I put in L3. Zoom 9, and that gives me the residual plot. Okay, so that's one way to do it. The other way to do it would be to go back to the Stat Plot menu, turn on the Stat Plot, And this time, instead of using L3, I'm going to go and take advantage of the fact that every time the calculator computes a linear regression, it also computes the list of residuals, and it stores it in the calculator. So the warning here is you have to do the linear regression first on your calculator. And then when you push second list, you will see at the bottom here is something called resid. Now you only get a resid after you do a linear regression. So just to contrast things, I'll change this into, let's go magenta, and we'll do the exact same thing, zoom 9, and here is my linear regression. These two graphs look the same because they are the same. Which one do you want to use? Totally up to you. Lastly here, we have, what does the residual plot indicate about the appropriateness of the linear model? Well, do you see a pattern? Is there a positive, negative, positive pattern? No, there isn't. So since there's no obvious pattern in the residuals, we can say that the linear model is a good fit to the data. And to convince ourselves even more, here's a picture of the scatter plot of the x coordinates and the y coordinates. This is a scatter plot of the weight versus the body weight versus the backpack weight. And yeah, that looks pretty linear to me. Now, a couple of caveats here for you. When you are making your plots, you do need to make sure you mark your x-axis, and you want to mark your vertical axis. And that should do it for us. Well, that's our look at residuals. Hopefully you understand them more. Hopefully you understand how important that residual plot is. And we will see you next time here for more on our AP statistics.